Good afternoon, everyone. It's another CS 340 lecture. Yeah, as always, Payman is here to represent you. Please keep your questions flowing and interrupt as and when is necessary. And Payman, obviously, if I say something that's stupid or it doesn't make sense, please keep me in line. Okay, lovely. Let's do this thing. Today we're going to talk about data exploration, roughly. But first, let's start with some admin. Assignment 1 is due next Friday. We already said that. It's out there. I see that people are starting to work on it. That's great. Start early. Don't delay. The grade scope submission instructions are on the course website. The access code is here. That's your access code for Gradescope. Use gradescope.ca, please, not gradescope.com, the Canadian version, please. You have to use your UGradCS UVC email address to identify yourself on Gradescope. We had a fiasco last year when people used multiple identities and their grades got split between 3 non-cross-referenceable identities, and people got bad grades in the course as a result. And then the dean got involved. Let's not have that. Failure to properly identify yourself. No, it's not going to be allowed. You get a 0 for your homework and exam submissions if you submit them under a different identity. Bookmark the course webpage. Presumably you've all found it at this point. If we can figure out a way to automate the lecture recordings being stuck up there, we might even do that, but I have no plans to do that at the moment. So lecture recordings are still on Canvas. Everything else is on the course website. Tutorials and office hours have begun. No, there should have been a video recording. If there isn't, then there's some technical error that's not my fault for once, actually. And there's always the recording from the other section as well. You sign up again. Yep, great. Wonderful. Okay. Thank you for resolving that. And sign up for the course if lots of people are using it. That's good. Okay, today we're going to talk about data mining for the only time, and maybe really data mining and machine learning. But from a bird's eye view, what's data mining, or what does it seem like it should be, right? You go off, you collect some data, you do data mining, yay, and profit. Yeah. Turn your consulting gig into $5 grand and buy a bicycle. Okay. Unfortunately, data mining and machine learning are quite a lot more complicated, because it's not just collect data, do data mining, and then use the results for profit or evil or whatever you want to do. Instead, you actually have to spend a lot of time learning about the application, identifying the actual task that you can do inside of the application. You have to collect a bunch of data. You can, you collect the data to solve that task. You clean, pre-process the data, you transform the data, select useful subsets, you choose data mining algorithm, or machine learning algorithm. Then you can actually do the thing. You can press go. Then you have to evaluate and interpret the results. And then you can do something, but actually not even really, because ultimately you'll almost always have to go through cycles of this kind of a thing, often involving lots and lots of messing around with your data, cleaning and pre-processing it in order to put it in a form that actually is useful for the thing that you want to do. And that's going to involve transforming the data and selecting useful subsets and so on and so forth. Okay, so there's some question. This is so Gideon, this is the kind of question you should ask on Piazza instead of during class, I see, and Payman, don't forget to bring these to my attention because I'm not paying attention.
Yeah, I was just right.
Exactly. But to answer it anyway, Payman, can you have more than one assignment partners for each assignment? No, you have no partners for the first assignment and then one partner for subsequent assignments, but it doesn't have to be the same partner. Okay. So what is data? It seems like a pretty obvious question, but actually the way we treat data here is relatively particular, which is to say that we'll define data as a collection of examples, or I quite often call them samples, but examples and their features, okay? So each row is an example and each column is a feature that should be built in here. Yeah, so each row is an example and each column is a feature. Now, what you need to get into your head is that this feature word is actually pretty important, right? So imagine that, this is Payman here, and this is, Sarah here. Okay, these are individuals, right? And these individuals have features, and that's actually where the word comes from, right? So Payman might be 22, I don't know. He might be unemployed, I don't know. He might live in Vancouver, and he might have a very poor credit rating. Sorry, Payman. You are TA, you're not making a huge amount of money, that's for sure. Sorry about that too. That's just the system. And Sarah might be 22. She might have a job. She might also live in Vancouver and might make some amount of income. Okay. So the point is that we have individuals. They're examples or samples or rows in a database, or rows in a comma separated value format thing, or rows in an Excel field. And the columns are going to be the features. So age, again, gender, job, city, grade point average, whatever. These are going to be features of the individual data items, okay? And a lot of, you really need to get comfortable with this idea of, and terminology of feature right away, because we're going to use it a lot in the class, okay? There are lots of different types of data, right? Like in particular types of features, really, that's probably a better way of saying it. Like the features of individual samples or examples can come in the form of categorical features, which come from some sort of unordered set, like does somebody have a job or not, or a nominal set, a nominal valued set, which is to say which city do they come from, Burnaby, Surrey, Vancouver, so on and so forth. Numerical features, things like age, mine is very high, yours generally is pretty low. Ordinal, some sort of rating, how much did you like this movie or not, or continuous or real value, which could be height or weight or something like that, right? In general, in this course, we're going to work on numeric valued feature vectors. So where every sample or example or whatever is going to correspond to a long vector. Generally speaking, each of the elements is going to be numerical in type. Okay, this is because we're going to want to be able to do mathematical operations on those that requires them to be numerical. Okay, so if we have a table of examples and features, whoever is unmuted, please mute yourself. If we have a table of data items like this, in which we have three features, one of which is this ordinal feature, city, Vancouver, Burrard, Burnaby, Surrey, so on and so forth. If we want to operate on numerical features, which we're going to want to do, we can't actually operate on a data type that looks like this. So we need to actually transform it into some sort of a numerical representation. And one way to do this is to use a so-called 1 of k encoding. So if we have k different cities that we have in our data set, we can simply transcribe the city value into a one hot vector, indicating that this first individual lives in Vancouver, so on and so forth. The second individual lives in Burnaby, and so on and so forth. What's nice, and one of the things that we're going to do is again, convert everything to numerical features when we can, is we can interpret each of these examples or samples as a point in a high dimensional vector space.
Someone's asking, is 1 of k encoding another name for one hot encoding?
Yeah, basically, yeah. Yes, and could you use a different value besides 1? Sure. And most models, it doesn't really matter at all, because for instance, as you'll see later on, one of the most common things is to use a linear linear layer or a linear model in which you have a parameter per feature vector, feature dimension, in which case if this is 2, then you would just scale the parameter value down by half and you would have the exact same model. So you can use whatever values there you want to. K unique features. Oh, sorry, yeah, sorry. The K in 1 of k means k distinct or unique features. Yeah, basically. Cool. Yeah, keep just payment. Just jam them in there. That's okay. It's totally fine. You let her rip.
All right.
So we can interpret these vectors per sample or example as vectors in this 5-dimensional space, right? Okay, and then that means that we can do things like take dot products of them, and we can measure the lengths of those vectors. We can take angles between them, so on and so forth, right? Great. Cool. Surprisingly, you can take a large number, basically any kind of data type can be represented in this kind of numerical feature vector kind of a thing. So let's say, for instance, you have little text snippets about academic conferences, and you want to do some sort of machine learning where one of the features of the data that you're looking at is this text snippet. You might say, how am I possibly going to encode this, right? So one thing that you can do is you can encode text. This is not the only way to encode text, but it's quite a common way of doing it. You can encode this text by turning it into a bag of words representation, where you say, for instance, take the 5,000 most common words most commonly used words in a language. That's your dictionary. Ignore everything else. And the representation for this particular feature would be just going through and ignore the, because the stop word. You count international. How many times is international? International appears twice. ICML appears once. Conference appears twice, so on and so forth. And you just count up the occurrences of the dictionary words, and your feature vector corresponding, the transformation of this text into a feature vector corresponds to simply putting the count of the number of dictionary words that occur in this particular text snippet into the corresponding dictionary entry dimensions of the feature vector, right? Of course, this is maybe not the best representation of this this text. It ignores order, but often actually such a bag of words encoding captures the general theme of a text document, right?
Some of them, I think, can we map cities to values instead of using multiple dimensions?
How do you mean? Yeah, okay, sure. So like, Henry, I see. Yeah, obviously you could encode cities if, for instance, you had some sort of prior knowledge that suggested that, for instance, the geographical location of a city was important for making some sort of prediction. You might encode Burnaby and Vancouver based on their GIS coordinates or lat launch coordinates or something like that. Sure, absolutely. If you were to give them actual values rather than one of K encodings, that would be a little weird. In most cases, you could do it, say, for instance, if you're using random forest, but it would be a weird thing to do. Yeah, is there anything else?
It's called label encoding. That's called label encoding? Oh no.
Yeah, I mean, so sure, Siddharth mentions that you could call this label encoding. It kind of doesn't really matter. Ultimately, we're going to figure out ways of automating what these features are and the derivation of these features from raw data types. But indeed, if the categorical value or the discrete value carries some sort of ordinal information or ordered information, then yes, you can. It becomes much more reasonable to assign it a numeric value, even if the numeric value doesn't have the same semantics as, say, for instance, A, something like that, as a grade. We can also approximate or represent images or graphs as in vector representations as well. One way to think about images, if you haven't thought about this already, forget this is a color image. Think about this as a grayscale image. And just take, for instance, the first pixel value, the second pixel value, so on and so forth, and just flatten this entire image by basically taking one row at a time and building, if this is m rows by n columns, an m by n long feature vector of the grayscale values for every one of the pixels. Okay, now we can make a big feature vector, and now we can put, now we can compare images, maybe not again in the most awesome way that you could possibly ever want, but you can compare images or compute distances between images in this vector space. Same thing with graphs, for instance. You can take a graph. I assume that Payman is a very popular individual and has a huge, social network presence, and has lots of Twitter followers and Facebook, groupies and whatever they're called. I do not, but we might want to use the graphical representation of Payman's social environment as one of the features of Payman for some sort of task, like in other words, the in degree, the out degree, that's who you're connected to, so on and so forth. You could compare individuals based on their graphical relations, right? So one way to encode a graph is just to actually encode the adjacency matrix, right? So if you choose a particular node, then for N1, you can look and just encode into as one way of representing the graph, all of the other nodes that it is adjacent to, in other words, the nodes that it's connected to by an existing edge, right? This is one way to encode this graph as one of these long feature vectors, where again, the number of dimensions would be the number of nodes in the graph, and there would be 1 or 0 only if there's an edge between them. Okay.
So someone wants extra explanation on how to flatten an image?
Write a for loop or a nested for loop that indexes over the m rows and the n columns, and then for every one of these, you just put it here, and then the next one you put it there, and the next one you put it there, and when you get to the end of m, then I guess it's this is going column first, I guess. I apologize. So whatever, it doesn't really matter. Then when you get here, you put the next one in there. So it's over. Just wrap around. Hopefully,
yeah. Then if it's a color image, would we instead use a tensor, or we can use tensors for?
This is the problem with modern deep learning packages being available. People think they know what they're doing straight away. So if it were a colored image, you could either first transform it to grayscale, or you could do the same transformation with all of the color channels and represent the entire image as just one very, very, very long vector, 3 times m times n, for instance. Yeah. Anything else out there that I missed? Chen Zi, thank you. What if the image of each example has a different size? Oof. Give up. Let's just assume that the images are all the same size for the time being. We can deal with that later if we have to. So we've just covered sort of how do we take a number of non-numeric types and turn them into numeric features so that we can do machine learning and data mining, whatever that means, right? A warning that we should put in front of you is that machine learning and data mining typically assume clean data, right? And we're going to actually effectively from this point forward in the course just assume that the data that we have is clean. Whatever clean is, not dirty, doesn't have errors and that sort of stuff. So let's just think about ways in which the data might not to be clean, right? Various features or the entire sample or something like that could be distorted or be noised in some sort of a way. There could be outliers that are caused by measurement error or data entry errors. There could be missing values simply because the data is not available or it's not applicable in a certain situation. You can be duplicated data. In other words, why do you need 2 columns with the exact same data? It's unnecessary. They can be different storage formats, so on and so forth. Any and all of these are going to cause problems in reality and will cause you to loop in this data mining, machine learning, doing it in the real world thing, right? Generally, it just is like consulting advice to you if you go off. Generally, you want to fix these issues if you can. Some machine learning methods are robust to sources of noise in the data itself. Often, actually, machine learning tools are the way to actually go about detecting and fixing these errors, particularly if you have a very large data set. But such it is. So now we've got feature transformations. We can get everything in numerical. We're acknowledging the fact that data is quite often noisy. And then the next question that a lot of people think is, okay, we're going to be doing data mining or machine learning. Certainly you get this if you go work at a consulting company or you do some consulting yourself. The question is like, how much data do you need? And Akim has answered it more or less exactly. Invariably, 3 or 4 people will ask this question as the course goes on, and I'll just get annoyed and give you the exact same answer, which is that we don't know. Who knows, right? There's no right answer to this question. The usual answer is more is better, as much as possible, so long as it doesn't get noisy and really crappy and doesn't cost too much and that sort of stuff. Another popular answer is some multiple of the number of features that you have. Something to think about. And it's like a little intellectual exercise that we can put out there. This is one of these funny colored slides. Can you tell the difference in the color? No, not really. So this is one of these, you don't have to learn it, but just get a sense of what's going on, right? Let's say, for instance, you want to do the average BMI of all of the, in each state in the United States. Okay, like you'd like to know what the BMI is in every state in the United States, right? And the question that we have here is like, this is related to how much data do we need? Like the question is, how much data, how many people, if we were to randomly sample people in the United States, how many people would we have to ask in order to construct a good estimate of the average BMI in every state? Good question, right? So let's make a totally unreasonable assumption and say that if we sample from the 300 million people, and we just drew people at random, we would hit a particular state with exactly equal 150 probability. Okay, that's not true, obviously, because there are different populations in different states, but let's assume this, right? So the question is, in this contrived setting, how many examples, how many people do we have to poll in order to actually get one person from every state? Right, which is like, you need at least that much data to say something about how much somebody in Alaska weighs. Or sorry, not how much they weigh, but what the BMI is, excuse me. Well, the answer is that you need about 225. You need to pull 225 people. This is an instance of the coupon collector problem, and the answer is if you have n possible bins, you need in general n log n order n log n in samples in general. And of course, there's an obvious sanity check, which is that you can't really state anything about the BMI in Alaska without having at least one data point from Alaska. And in actual fact, you probably want to actually ask 5 or 10 people in Alaska, or maybe 100 people in Alaska. So in order to draw any sort of predictive statistical conclusion about what's going on in a particular subregion of your feature space, you need a relatively large number. You need to query a relatively large number of examples, right? Cool. All right. Other things that we can do. So this coupon collector problem is like the first insight that we're going to have in terms of like what we would kind of refer to as overfitting, or having insufficient data to actually draw any sort of conclusion about some particular setting of a feature vector. So here, for instance, maybe we want to make very particular, maybe we're making some sort of prediction about, who knows, people's income, and some of the features that we have are the specific cities in which they live. But let's say we have a relatively small data set, and that means that we don't have very many instances of people who live in Surrey, right? So something that we can do in order to try to improve the predictive accuracy of our model is to reduce the dimensionality of the feature space by, for instance, combining all of the BC city features and all of the Alberta city features into feature vectors, or features that just say that a person is in BC or a person is in Alberta, such that if you made a prediction about their income or whatever, you would need a relatively smaller amount of training data, because the probability of getting data, or the presence of data that is in BC versus Alberta is higher. It's not so subdivided, if that makes any sense. Great. Payment, question?
No, I think we're good.
Okay. You can ask questions too. You're, like, I get to watch your face as a general, that's the face I get to see. So I see your face and you're like, I don't know what's going on. So you should, if you don't know what's going on, I'm not making sense. You got to be the one, right?
All right.
How do you decide how many features to aggregate? Okay, so all of the questions of this particular type, thank you, Alan. All of the questions of this particular type for now, there are two answers. One is a 3, but they're really all coming down to the same thing. We will establish ways to tell how well your models are working, and you will select amongst models in a way that attempts to generalize well. So you can think really hard about what features should be included and when you should aggregate and when you should not, and you should just think about it, and maybe this is good. Second, later on in the course, we'll talk about ways of automatically aggregating features and automatically selecting features. Third, we'll talk about models that are capable of operating even when the values in features are sparse in the sense that we've just been talking about. But in general, you can either think hard and impose problem-based understanding to make decisions like the one you're just talking about, or we can design methods to deal with it automatically. And in both situations, the stick that we're going to use to measure whether or not we made a good choice is a predictive performance. Okay, so we'll get to that. That's quite a long ways away. But in the manner of like thinking in advance about what features you should stick in, part of the feature selection challenge, which we're going to talk a lot about features and feature selection in the course, like one of them is like, well, if you're doing some sort of prediction about, student future income, right? You might have a table that includes the student ID at UBC or something like that, right? Clearly, you don't want to keep this data around it. Any model that you could ever possibly use to predict income based on these features, if it used the student ID in any way, it would clearly be overfitting. It would be using data that clearly is not correlated to income. Student ID is not relevant. Of course, you could argue that maybe it is because maybe you get a big student ID if you register late, or who knows, right? There's probably hidden correlation there, maybe, but probably not. Sometimes, in order to make methods work better, you want to do feature transformations that include discretization or binning, which takes numerical data and turns it into categorical data. So maybe you don't have enough data to really do a fine-grained prediction based on a continuous age. So maybe you just want to look at age in 3 or 4 buckets or something like that. So you can do a transformation like what we see here. Okay. And we're going to see tons and tons more transformations that address all kinds of other problems. Okay. For those of you at home, watching TV, playing video games, and otherwise being comfy in your pajamas or whatever. This is the point at which I try to make you feel uncomfortable by pausing for a little while and getting you to ask questions. Are there any questions at this point? And I've been working on my uncomfortable dance, but I haven't got it down yet, babe.
So I have a question. If we do the feature selections and like dividing or whatever categorization, and we end up with a group with very small number of features, is it a problem? Like, do we have to choose another categories, or what's the solution here?
So is your question, what if is the question really, what if we do a bunch of, so I think I understand. So if the question is, what if we end up with a small number of features? Well, then don't do the things that you just did. Yeah. Right. So, and the larger answer is, there is no right model. We'll talk about a no free lunch theorem or whatever, right? We don't know what the right feature set is for most applications. It's very, very uncommon to know that. Basically, only certain physics and other science models do you actually know that, mass and velocity, are a pretty good way to compute kinetic energy or acceleration or whatever, right? We know that this relationship holds, and we know what the features are that we should use to compute the other thing, right? In most situations, we don't know, and all we really care about is predictive performance, right? So if you have good predictive performance from a very small number of features, great. If you don't, then think about it. Yeah.
So is this more qualitative, subjective, or we're gonna learn how to deal with it mathematically? Like I guess,
yeah. Okay. So this is a good question, Dominic. So the all of our discussions are going to be dominated by two things. One, the no free lunch term, which is to say that various machine learning, there's no way to know in advance whether a particular machine learning algorithm, there is no one machine learning algorithm to rule them all, and there's no way to know in advance whether or not a particular machine learning algorithm or model is going to be the one that actually works well on a particular data set or a particular task, okay? So we can't make general statements about like, you know, what is the best machine learning model, but what we can do is make mathematically grounded statements about individual models and their characteristics and their behaviors. So we're going to do that a fair amount, but it's impossible to make an overarching statement, basically. Cool.
Can aggregation help when the number of features is more than the number of examples?
That's a good question. Sure. Yeah, definitely. Let's talk about overfit. So I see there's a question about overfitting. Let's talk about overfitting later. I see the term feature extraction used a lot in image analysis where the features automatically generated during the training. What exactly are those features? How do they compare to more easily understood numerical features? Okay, this is an okay question at all. It's looking quite a long ways forward, actually to the very, very end of the course. What is a feature, right? Who the heck knows, right? It's a feature is in the eye of the beholder, right? So you hear about feature extraction. Well, really a feature is just a function applied to, like, you can think of a function as being a feature as some function applied to a raw observation. That's it. So for instance, if you have a convolutional neural network or something like that, you can say the features of an image are just a random weight convolutional neural network applied to an image, and that's going to give you some vector representation of the image. That is the feature representation of your raw observation. Sometimes your raw observations are the features. Sometimes you compute derived features by extracting features by basically applying a function to a raw observation or applying a function on top of other features, right? So basically, at the end of the day, for this course, features are the things that are fed into the machine learning model, whatever that happens to be, right? And feature extraction is whatever non-trainable component is imposed before it goes into the model. Deep neural networks conflate the two in a way that's extremely promising and profitable, which is to say that the network extracts features and operates on those features to produce a classification. But that will be at the very, very end of the course. Yeah, feature extraction. Okay, I don't see. Tianyi, do we have to consider whether two features are not independent? It's correlated features. Some are problematic for some machine learning models and are not problematic for others. So it depends on the model that you use to solve your task. For linear models, sometimes. In general, it's a good idea to remove redundant features or correlated features, or yeah, exactly. Perfectly correlated features are somewhat problematic. It causes a low rank issue, but we'll get there. Don't worry, we'll get there. Just for a second, before we actually get into sort of machine learning methodology, let's pretend that we're all actually doing machine learning or data science. And let me just remind you, we're going to have Kaggle competitions where you have to actually prove out what you know and what you've learned in the course. And the first thing that you should do, just bang this into your head if you're going to go off and do machine learning rather than understand it and design new algorithms like we talk about in this course. The first thing you should do is look at the data, right? So how do you look at features and high dimensional examples and get a sense of what's going on in the data? You compute summary statistics, you visualize stuff, and in fact, you use the products that we're going to talk about later in this course, machine learning and data mining. So what kind of summary statistics can you compute for categorical data? Summary statistics for categorical features include frequencies of different classes. The category that occurs the most often is called the mode. Categories that occur more than t times are the quantiles, right? So here's the population by year, by province and territory of Canada. Like you can look at the frequencies, like 13% of Canadian residents live in BC. Ontario has a large number of residents, so it's the mode, and quantile, 6 provinces have more than 1 million people. for instance, right? There are continuous summary statistics. Most of these should be familiar, so we can go through them very, very quickly. These are basically measures of location for continuous features like the mean, which is the average value. That's the standard maximum likelihood estimate, right? The median value is such that half the points are larger, half the points are larger or smaller. Same thing. And quantiles is it's the value of the kth quantile is such that the kth fraction points are larger, right? So measures of spread for continuous features include range, variance, and interquartile ranges. Just remember, the square root of the variance is called the standard deviation. Okay, so let's take a continuous data set here. These all happen to be integers, but they're continuous. So continuous summary statistics, and look at what happens. This particular data set has a clear outlier, and we put this here just to make sure that when you're thinking about these statistics and what they tell you, that you should be aware that some of these statistics are sensitive to outliers. So measures of location, if you take the mean of this data, add it up, divided by the number of data points, you get 21. The mode of the data item that occurs the most frequently is 3, and the median is 7.5, right? The quantiles of the data, the 0.5 quantile is 7.5, so on and so forth, right? Measures the spread, the range is the max and min of the data. The standard deviation is kind of ugly here because the variance is so large because of the outlier, right? And the interquartile range of the data between the 25th and 75th percentiles is 11. So this gives you a sense of what's going on. You can compute this for various features just to see what's happening. And you should note that the mean and standard deviation are sensitive to extreme values. And this is going to show up when we talk about L2 norms later in the course. Something that's relatively unfamiliar, usually at this level with the people that come into the course, is the concept of entropy, which is a measure of randomness. And I refer you to Cover and Thomas or David Mackay's Information Theory and Applications book to really go into the depths of this, or take an information theory course. But a common summary statistic for populations, and we're going to talk about discrete entropy in this course, and never differential entropy. The entropy measures the randomness of a set of variables. It really is a functional on discrete distributions for us, but we'll think of it as a set of random variables. Roughly, it's another measure of how disordered the set of values is, or how non-uniform the set of values is. So formally, how many bits of information are encoded in every example? For a categorical variable that can take k values, the entropy is defined by minus sum c equals 1 to k of the population proportion, the probability, the proportion of times that you have value c in your set, times log of that probability. Okay, and we'll talk about this in just a second. Low entropy means very predictable, right? That means that out of the set of numbers from 1 to 10, if your observed data only has 5s in it, and you're asked to predict what the next number would be given the set of numbers, then it's pretty easy. You just predict 5. But if it is uniformly, values from 1 to 10, then and you're asked to predict what the next value is, it's very hard to make that prediction because that's a high entropy distribution. Okay, so the minimum value of entropy is 0. The maximum value is log k. And we use the limit definition of 0 log 0 equals 0. So just to drive this home a little bit, a low entropy distribution. So here we have a set of this is a histogram on the values 1 to 4. So this is some set of values in which all of the values are 2. If we compute the relative proportion, p of 1 is 0, p of 2 equals 1, p of 3 equals 0, so on and so forth, then we can see that this is a 0 entropy distribution, right? It's the lowest entropy you can have. A high entropy distribution means that the values in this set are very mixed and are uniformly distributed effectively across the various options. So if you compute the population estimate of the proportion of 1s in this set and the proportion of 2s in this set, so on and so forth, i.e. the probability of encountering them in the empirical sense, then this is a high entropy distribution. So for categorical features, the uniform distribution has the highest entropy. Like I said, we're not going to talk about differential entropy at all in this course, but it's Interesting to note that for continuous densities with fixed mean and variance, the normal distribution is the highest entropy, and that is super not obvious. And you can do interesting reading about, like, for instance, I guess it's I guess it was Shannon himself who estimated the entropy of written English. So you can go off and actually estimate, like, and when you evaluate models like GPT-3 and that sort of thing, you evaluate them based on the entropy of the predictive distribution, right? So if you have a low entropy predictive distribution, that means that you're very confident about what's coming next. And if you have a very high entropy distribution, it means that you're very unconfident about what's going next. And you can actually compute the entropy of the English language, or estimate it, and it is estimated to be about 1.8 bits per character, or 1.6 bits per character, excuse me, which is kind of interesting to think about. Anyway, we're going to have to deal with distances and computing distances in both feature space and in sample space. Some notions of distance that we want to pay attention to. So there are some summary statistics that we can compute between, say, for instance, features X and Y. One of them is a Hamming distance, so you can just compute the number of entries of, oh, that one's okay, I don't know how to erase. And so I'll do that. The number of entries that are different between the two. Euclidean distance, you should know how to compute the, oh man, Payman, you gave me, you missed a question. You're doing, I don't know what you're doing.
No, I just wanted to let you to finish.
No, don't let me finish or interrupt, man. It'll be way more fun for everybody if it just, like, none of the, plus it's also a lot easier for me to keep track. So yes, the range or values of the feet. So the question is, does the range or value of the, you know, like if the, yeah, I don't want, I have to read it so that I have it in the recording, but if the set of values is 1, 100, 100, 100, or versus 1, 2, 2, 2, 2, do those two distributions have the same entropy? And I hate to say it this way, but yes, they do. They have the same entropy because the entropy is a functional of the probabilities, not of the values, right? And the sets don't have to be numeric for that. That's certainly true. And again, there's a little bit of hand waving on that, and it's worth checking. The entropy is a function of the probabilities, not of the items, and the probabilities are computed as proportions in this particular set. You have a data set, and there's proportions of the individual items, right?
What is feature space versus sample space?
Yeah. So. Great. Yeah. So a feature space, for instance, just and I probably shouldn't have said it at this point in the course, but a feature space, there is a vector space in which this X feature can live in, right? So if every value of this X feature, this is an n-dimensional vector rather than a d-dimensional vector. So if we have d features and n samples, right, then X lives in some, here we'll say 0, 1 to the n, right? So that would be the feature space for this particular feature, right? So what we're talking about right now are we're talking about really just different ways of computing distances between vectors in arbitrary spaces, right? We happen to be talking about them in feature space right now. So we have two columns in the same feature space, and we want to be able to compute the distance between them. So one thing that we can do is we can compute a Hamming distance, which is just sums up the number of elements in the vectors that aren't equal. We can also do Euclidean distances, which you should know what that is. We can compute correlations between them. Does one increase or decrease linearly as the other one increases, so on and so forth. There are other kinds of ways of thinking about statistics that we can compute between features X and Y. We can look at the rank correlation. But also we can think of it if these are, for instance, sets for whatever reason, like items in a shopping cart or something like that. We might want to compute a Jacquard coefficient, which measures the distance between two vectors as the size of the intersection of the sets over the union of the sets. So that can be computed in this representation. And we can talk about edit distances as well between strings. Again, this is one of these off-colored slides, so you don't have to worry about it too much. I think we'll actually touch Jacquard coefficients later, so you should definitely look them up.
What's the difference between edit distance and Hamming distance at the bit level?
Uh, 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 technically speaking, and don't hold me to this, if the strings are the same length, whatever the number is you get from the edit distance and whatever the number you get from the Hamming distances, they should be equal up to some scaling constant. Probably the scaling constant is 1. Edit distance allows, generally speaking, depending on the operators that you allow for your edit distance computation, it allows for strings of different lengths, right? So that means you can have insertions and deletions of characters, and that is that there's a valid notion of distance there, right? That is very different than Hamming distance, because if you have binary vectors of different lengths, you don't know how to deal with the fact that the shorter vector doesn't have entries where the longer vector does. So I hope that's clear enough. This is not going to be critical for our course, but that's the biggest difference. Hopefully that's okay, Alan. This is where the lack of feedback really sucks, but I'm doing my best. There are some limitations of summary statistics, and we're running out of time. So let's put it this way. When you compute summary statistics, you should be careful, because you can arrive at situations where the same data set has very different summary statistics. So this is Encombe's quartet. If you actually look at this data right here and you compute the means, variances, and the correlations, they all are basically the same. But if you were to run a machine learning model having looked at the data and analyzed the data, having looked at the data beforehand, you might recognize that there are outliers in these particular data sets, and you might change your model rather dramatically, given the insights that you get from looking at the data rather than summary statistics. Okay, cool. This stinks because somehow we've managed to go much slower in this lecture than the last one, but we'll work through it next time. Let's see. I'm gonna do 2 more minutes because nobody actually has to go anywhere. They can just commute from their thing. So we can learn a lot from visualizing the data in advance as well. So you can learn a lot from 2D plots of the data. You can identify patterns, trends, outliers, and unusual patterns. So we're going to talk about data in this form. There's going to be vectors, so on and so forth. But in fact, actually, maybe the lat long attempt actually corresponds to some world map and the temperature of the world map. In that case, it may make sense to look at things in this particular way to see what's going on with the data. All of you should know what a basic plot is, right? So maybe we look at the runtimes of various sorting algorithms as a function of vector length, or so on and so forth. You have multiple plots on the same thing. All of you should also be comfortable with what histograms are, right? So here's Payman out here with lots and lots of friends on Facebook, and here I am over here. And this is basically the population frequency of people with this number of friends on Facebook, for instance. Box plots should also be familiar to you. You know, when you're looking at a data summary in this way, a box plot has the median here, the upper and lower quartiles, and then the lowest and highest values, right? These are used all over in science publications, and even show up on Canadian coverage of the Olympics when you're talking about projected medal counts. One of the things that you should definitely do, and is often overlooked until somebody puts it in front of you, and here it is in front of you. Quite often we're going to be looking at the data table. Again, we have samples here, and we have features across here. One thing that you can do is just simply actually look at your entire data set and plot it as an image. And sometimes you can see trends in the features. You know, for instance, these are all high value features. These are all low value features, so on and so forth. You might be able to get something you might be able to get some understanding about your problem by looking at your data in this particular way. Another plot that you should be familiar with and comfortable with is this matrix plot, where you can look at, for instance, the similarity or distances between features. So if you have a bunch of features, you can look at, how similar how correlated is BTC with itself should be 1, with ETH, XRP, blah, blah, blah. There was a question earlier about correlated features. One way to identify correlated features is to actually plot the correlations like this in a heat map. And then if there's a highly correlated feature, you can say, well, actually Dash and ETH, whatever these features happen to be, are super highly correlated. So we'll just use one of them, okay? Scatter plots, all of you should be very familiar with as well. You can look at one feature versus another feature. Again, payment over here, me over here. If you can't tell, this is personality going up and looks over here. Great. So this shows that there is a correlation between personality and looks. And this is a really damning indictment of humanity, but that is what it is. Scatter plots allow you to see pretty complicated patterns. They can give you hints, for instance, that you should use certain kinds of features in your feature set. Last, we'll finish with this. It's pretty straightforward. Scatter plot arrays. So here's an instance of a scatter plot array where we're looking at classifying a particular kind of iris flower into a number of species, and we have 4 different features: sepal length, sepal width, and petal length. And what a scatter plot array allows you to do is look at each feature against the all other features. So this is petal length versus sepal width. This is petal length versus sepal length. And looking at data this way can help you design algorithms, say, for instance, classifiers. So if you were to just look at sepal width versus sepal length, it's not clear how to build a classifier, but you could imagine writing a program straight away that was able to pull off this green species from the others by just looking at the petal length versus sepal width perspective. Same thing here. You can build a classifier that just divides in this feature space. So we'll leave it here. There's just a little bit to catch up on, maybe 5 or 6 slides. I encourage you to maybe look ahead, but we should finish up here and then pause for questions. Thank you.
Is the scatter plot array like the correlation plot?
No, not really. So the scatter plot array is it's just feature versus feature, right? And the correlation plot is compute the correlation between one feature column and another feature column, right? So this is a summary statistic that says, is the feature column BTC, sorry, that's a dumb one to look at. Let's look at this one. Is the feature column LTC versus the feature column XEM, whatever these happen to be, are those 2 columns, the values in those columns correlated? So you just take the column XEM and the column LTC and compute the correlation between them, and that's the number that goes right here. Okay? That's quite different than the scatter plot array, which is feature versus feature for all pairs of features. More questions? Oh, everybody, you're quite welcome. Sorry that we can't be together. It's way more fun for everybody. Okay, if there are no more questions, we'll let everyone go. Thank you, Payman. Lovely to see you. Thank you all. And I look forward to doing this again on Monday.